Thank you. Thank you, Sergey. Thanks for having me back. Thanks, all of you, for coming. My name is Human. I'm the VP of Technology at Fastly. It doesn't actually matter. I'm going to talk to you about H2 today, or HTTP2. And before I start, just show of hands. How many people know H2? How many of you know enough about it to get up here and do like a 5-minute talk? That's what I want to see, Adler. That's what I want to see. And how many of you are using it? So that's more hands than the people that knew about it. Okay, and how many of you that are using it are elated and think it's the greatest thing in the world and are super happy? Huh, interesting. Okay, let's start. I have a lot to talk about. RFC 7540 ratified H2 over 2 years ago now. And it's been in the wild for a while. We've talked about it a lot. There's been a lot of hype. Pretty much every client now supports it, if you look at it. There's a couple of little outliers in there. Every server that I know of, or every significant server and load balancer supports it as a protocol, as does every major CDN and cloudy load balancer type stuff. I was very curious about adoption, and not necessarily a lot of people talk about adoption. I have the luxurious position of sitting on a network, however, that has a lot of million requests per second. That's a normal day for us. So, and we have some metrics. So I did some looking, and this is the adoption of H2 in 2017 for us, which had ended right around 30 to 35%. I checked today, it's around 40. And we are an opt-in service for H2, as opposed to like we're not a CDN that turn it on across the globe. So we didn't go from 0 to 100 or 0 to every browser that supports it. We have an opt-in model that will probably over time get phased out. But this, the reason I like this is a good indication of interest. People that have gotten interested and have decided to deploy it for one reason or another. Any guesses, by the way, of what the TLS number is right now? If you had to guess, what percent of the network of that 6 point whatever million requests per second do you think is TLS? If you had to guess. 50? Higher or lower? Higher or lower? Yeah, it's close to like 80. Which is, I was shocked to see it. It's impressive. Now, granted, all of this is TLS, right? So it's at least this plus whatever H1. Now, when I look for trends, probably like you, we go to HTTP archive. And the irony is HTTP archive in the request tables actually has an HTTP protocol version column, but the double irony is that it's broken. So you can't actually query it for the HTTP version, but there is a thing called average number of connections per site. So I did a little thing where I looked at the average number of connections per site. And you'll see that at some point in 2016, the number dropped. Now, it would be easy to look at this and say, that's got to be H2, because it's less connections, and that's what's happening. I'm not sure that's really a conclusion to draw here. This may be more correlation than causation, especially since there's a sharp drop. You could delude yourself more that it's all H2 if you do this, which is overlaying performance on top of it. Now, it's okay to do stuff like this and look at graphs like this, but necessarily deciding that this is all because of H2 without knowing is not really a good idea. Yeah, was it that far ago? Was it a year ago? Really? I thought they went to Chrome. That was okay, see? That's why you can't think that this is because of H2. So looking at stuff like this, and a lot of, at the time, which stuff that seemed like propaganda almost, really kind of seemed like it put H2 on a pedestal. And I'm all a fan of hype and glory and great things, but I kind of like to, I was curious enough to want to look at it from a practical standpoint. So I did a bunch of research, made up a bunch of slides, and I went on the road and did a few, who remembers the tick? Come on, you got to remember the tick. I love you guys. I can look at this all day. That's a link to the talk. I did this talk about like the practical implications of H2, did some performance testing, did like a whole bunch of data gathering, talked about it quite a bit, tried to teach a little bit about H2 or what I knew in the process of learning. I tried to sort of pass it on. And that was now about a year and a bit ago. And the impetus for this talk was, let's try to revisit that. So the idea here isn't necessarily to rehash those topics, although some of it will be rehashed out of necessity, but it's more to look at, has anything changed? I sort of left that talk with a takeaway that was like, we need to learn and we need to iterate and we need to figure out more. And this is a good time to at least ask whether we're on the right path or not. So what I'm going to do today is I'm just going to go over core concepts. So if you don't know H2, hopefully by the end of this, assuming you stay awake, you will know some things about H2, at least enough to really chat it up at parties. I'm going to go through some major features, and then I'm going to talk about if there's anything new, things that you should be on the lookout for on the horizon, and what's next. Now, I come to you not with an agenda. I am not, I have no hidden motive here. You will notice a lot of snark, but I don't have any, I'm not trying to convince you to do anything. I'm merely an observer and a presenter of facts. I happen to be in a position where I can see a lot of traffic go by, so I'm going to show you some things about that traffic. I'm a curious person, so I'm going to share some things with you, but I have no agenda. I'm not an IETF anything. I barely get invited to the parties. So I'm just going to share some things, and my biggest takeaway here is it's usually best to decide for yourself and not listen to people, including me. Just take some facts and do with that as you wish. Okay, ready? Put your seatbelts on. We're going to go. First, let's talk about the basics of H2. H2, as you probably know, is a binary protocol as opposed to H1, which was a text protocol. We have some binary protocol fans. Lets you know that you're in the right room. H2, the entire context of H2 is reliant on a single TCP connection. We talk about the connection in H2 quite a bit. When H2 session starts, if you will, there's a connection that opens between a client and a server. This is a single long-lasting connection where everything happens over this one connection. So you have a single connection for the entire lifetime of your communication with that server. And theoretically, this is a better place for things like congestion avoidance and congestion management, and you're going to be able to handle traffic and network conditions a lot better if you're working under a single context. The protocol itself doesn't mandate TLS. There's actually a clear text version of the protocol, but pretty much all the browsers said we're only doing TLS, and they basically forced our hand. So the only version of H2 that you really see in the wild is going to be TLS. It uses ALPN, which is a new extension to TLS. Well, not new anymore, but it was at the time a new extension to TLS. Come in. And it says that over this one single TCP connection, you can actually reuse and use that connection for requests and responses that are on different hosts, as opposed to H1, where you open new connections for every host. We're going to talk about that later. So everything starts with a connection. On this connection, you have these things called streams. Streams are essentially virtual channels of communication that open between the client and the server. And streams can be opened in either direction. A client can open it, or a stream can open it, or a server can open it. And each stream roughly translates to a single request-response sort of transaction exchange if you're used to the way HTTP1 works. Every stream has a stream ID. The odd number streams are client-initiated. The even number streams are server-initiated. And 0 is reserved to signify the connection itself. The protocol allows for 2 to the 31st power of number of streams, which is like 2-point-something billion. So you can't reuse the stream IDs, but chances of you running out of stream IDs is not very high, and they just have to be incremented. You can go backwards in streams either. If there was any doubt by this point that the glory days of the stateless protocol that was HTTP1 are behind us, you can be reminded that H2 is a very stateful protocol if you look at the state diagram of a stream. Every stream has a state diagram. For the next 20 minutes, I'm going to delve into each of these boxes in great detail. I'm kidding. The smallest unit of communication in H2 is something called a frame. So what happens is actually the bits on the wire are frames. And frames travel back and forth between a client and a server. And the way that you know which frame belongs to which of these streams, which are virtual communication channels, and every frame carries a stream ID, and that's how you know which stream a frame belongs to. Now, to visualize this a little bit better, imagine a request and response from H1, where in a request you send a bunch of headers, which are request headers. In a response, you get a bunch of headers, which are response headers, and a bunch of body. In H2, what happens is the headers get wrapped up in a headers frame, and in the response, you get a headers frame which has all the response headers, and then you get all the body chunked up into data frames. So that's sort of a high-level example of what these frames are being used for. The spec itself, 7540, defines 10 different frames. I'm not going to go into these frames, but they are each for a different thing. The three most important ones, the ones you'll probably come across most often, are these three. Data frames are used to carry data. Header frames are used to carry headers. And the settings frame is an interesting one, which is essentially the frame that carries settings, if you will, for the connection itself. So there's a whole bunch of meta settings that the connection itself needs to have between the two peers, and a lot of that stuff is communicated in settings frames. For you that like looking at packets, a visualization of this would be like this. This is old school. This is HTTP1. You have the TCP frame. Inside of that, you have the TLS sort of layer. TLS shuffles things back and forth in what are called records. Like an individual TLS record carries everything that's under it. And you have a bunch of text, if you remember in H1, back in the good days, where you had a bunch of text that basically was encrypted and transported with the record layer. In H2, things look very different. What you have is TCP and TLS, and inside the record layer, now you have these frames, each of them carrying a stream ID, and this is how communication back and forth happens between a client and a server. When you look at it like this, it's relatively easy to understand why some people, and by some people I mean me, I haven't heard anybody else say it, consider H2 more of a transport protocol for HTTP rather than a protocol in itself. And it's fair to sort of think of H2 as a transport protocol in its entirety, because nothing has changed in the semantics of the protocol. Headers are still there, caching is still the same, headers still mean the same thing mostly. But H2 now lets us sort of communicate back and forth in a different way. What's the protocol flow look like? Where in H1 it was like this: we had a connection, we sent a request, we got a response. In H2 we have a connection, and instead what we send is a headers frame with the request headers, and in response the server gives us a headers frame with response headers and a bunch of data frames with the data. And in H1, if you wanted to do more things than one, you couldn't do it, because on this connection you can only do one thing at a time. While that request was going across or the response coming back, you couldn't do anything else. This was a phenomenon we called header line blocking, which allowed no concurrency. This connection was tied up while this was happening. So how do we do concurrency in H1? Well, we opened a bunch of connections. Browsers typically open 6 connections, and that's how we got concurrency. In H2, it's a completely different paradigm. You have a single connection, and you have frames going back and forth. They can be from any stream. They can be from they can be going on either side. It all can be happening at the same time. Nothing's blocked. And this is what we mean when we say that H2 is a protocol that allows us to multiplex and interleave. It's this. We can have data frames from different streams going back and forth. We can have a bunch of header frames in a row, followed by a bunch of data frames in a row. There are some rules about what needs to follow what, but generally it lets us do a lot more at the same time concurrently on that stream. Somebody posted this picture as a good representation of H2 versus H1. I'm sure you are all extremely familiar with waterfalls, because you come here and Sergey will yell at you if you don't know waterfalls. This is what an H1 waterfall looks like, and this is the same page with H2. And for the two people here that look like looking at Wireshark, that's kind of what it looks like in Wireshark. And yes, Mike Adler, I have a color filter that is peach puke for H2. Okay, so while we're on the subject, let's talk about H2 and TCP. So one of the biggest features of H2 is this notion that everything goes over a single TCP connection, and because it's a single congestion context, everything's going to be better for performance. Let's put that theory into test. And this is what I did primarily on that earlier presentation that I was talking about. What I did was, okay, it's supposed to be this amazing performance gain for us. Let's test it with a perfect page. And I sort of constructed a perfect page, and by that I mean a page that has nothing, is basically causing no effort for the browser. It's just 100 images, No CSS, no JavaScript, there's no crazy rendering. It's just a single page, 100 images. This is what the waterfall of that page looked like with H1. This is what the waterfall looks like with H2. And the image that I chose was the same image over and over again. Unfortunately, it was this image. And this seemed like a really good idea when I started, but I did like 1.2 million tests, and I had nightmares about this dude. And the most unfortunate part of this is I did this talk 4 times, and for some fucking reason that I can't explain, the thumbnail that YouTube would choose to show this talk was always that same fucking slide. I have no idea how that happened. Somebody's got to be sitting somewhere saying, I know how to get this guy. So I took that page, and you all know about web page tests, so I basically ran it through web page tests a lot of times. I used the standard web page test traffic profile, which was 5 meg down, 1 meg up, 40 milliseconds of latency. I used Chrome, H1 versus H2, but the reason I use web page test is because it's got this cool feature that allows you to induce packet loss. This is the question that I had. Like, what happens if you have a single connection? What happens with packet loss? So this is what happened. I won't show you the hundreds of graphs that I showed earlier, but here's a scatter plot of H1 versus H2 for that one page with Chrome with 0% packet loss. The blue is H2, the orange is H1. You'll see that H2 sort of performs a little bit better. That's cool. It's not like the panacea that I was promised, but it's okay. But look what happens when I introduce packet loss. This is 0.5% packet loss, 1% packet loss, 2% packet loss. The story is very different, right? So that's interesting. Well, is this a Chrome problem? Let's try Firefox. Well, it looks like that's also kind of the same. Although maybe the advantage in no packet loss is a little bit more obvious. But still, maybe it's because I just bought into the hoopla. I'm not saying the hoopla is bad. I was kind of hoping for a bigger deal there, but this was the reality, at least for this page. Now, these are all incredibly synthetic and simulated scenarios. They do not represent real-world conditions. They're emulated, so that's a caveat that all this stuff comes with. At this point, I was like, okay, so this is supposed to do really well for really low bandwidth, high latency. So fortunately, web page test lets me do that too. So I did a slow 3G or a fast 3G profile, which has this performance profile. What did that look like? Well, kind of the same. Maybe a little bit more separation in the no packet loss situation. See that little bump up front? That was actually H2 getting turned off by accident, and it registered in the data. I kept it in there because it's kind of cool to see it in there. Same thing here. You see it here too. Because I like doing report cards, I did a report card. This was like the three of the core metrics that people look at when they look at performance and how H1 compared to H2 with or without packet loss. And then an obvious complaint against this is that this was a fake page. So I took a bunch of more realistic pages and did those 1.2 million tests, and it kind of looked like this. And this was like a big takeaway from the presentation that I did earlier, a year and some time ago. But this comes with a caveat that there are some problems with this methodology. And the problems are that it's all synthetic, it's all under not real world conditions, but still it appears that when there is packet loss, there is an effect on the performance of H2. Now, maybe the amount of packet loss I was inducing was too high, maybe it was too low. Whatever it definitely had an effect. And why did it have this effect? Well, it had this effect because this is actually grossly inaccurate. This is not H2 versus H1, this is H2 versus H1, right? Because we had 6 concurrent channels before that we've now replaced with a single channel. And look at what happens to TCP under packet loss conditions. This is the bandwidth, or CWIN, which is how much a server can send at every single round trip between a client and a server with 0% packet loss. And this is very normal. There's a drastic ramp up, there's some sort of loss event, ramp ups maybe slows down or drops off, and then at some point it sort of evens out. Look what happens to that with packet loss. This is standard TCP. This is the cubic congestion algorithm, which you've probably heard about. And there's a drastic drop to the performance of TCP when you induce, in this case, this graph's just 1% packet loss. This means that what's happened now is we've moved the notion of headline, the concept of headline blocking from HTTP where it was before and basically brought it to TCP. Now it's TCP that's the headline blocking component in the equation. And if you look at 6 connections being induced, having packet loss associated with them, and at any point you sort of add up the combined C-win across all of them, that is more than any one of them, so that's why you get more bandwidth through the pipe if you have 6 parallel ones. Now, there's problems with this too, but that's the reason that the problem was happening. These findings were not revolutionary, they were not drastic. In fact, if you haven't read this book, you should. This is mentioned, this is Ilya's browser, high-performance browser networking book. He mentions it in his H2 chapter that headline blocking has moved to TCP, and that's where it's at, and we know it. But the idea here is, despite this, the benefits of H2 are worth it, even though there's some headline blocking issues there. Yes, you have a question? Yeah, the difference being that UDP doesn't have built-in congestion avoidance and all the issues, right? So you have to build that on top of it. Right.
Get your choice.
Right. Yeah, this is what you get with TCP. This is TCP, so it's true. And standard congestion algorithms just use, drop packets as an indication of, or retransmits as an indication of what they should throttle. Again, this wasn't new. There's a whole bunch of other research on this that talks about this. If you feel like reading academic documents, please help thyself. At the time, the takeaway was that despite the problems or the methodology flaws, it appeared that the performance benefit that we think about when we think about H2 or thought about when we thought about H2 wasn't necessarily a slam dunk, and there were things to be aware of. And probably the best thing to do was, like I said before, I say here, not listen to anyone. Don't listen to people like me. Don't listen to anyone. It's always best to sort of see it for yourself. And the only advice I gave back then and the only advice I would give now is it varies. It may be great for you. It may not be great for you. And the best way to find out is try it. And if it's a thing for you, then go with it. And if it's not, maybe hold off. There's other reasons to go with the protocol that have nothing to do with performance benefits. I'm going to talk about that later. But that's basically the takeaway here, that the performance benefit isn't necessarily a slam dunk. And maybe it was because I bought into the hype, or maybe it was because I'm just a skeptic that I went down this route. But that's the idea. Now, has anything changed? Okay, that was like a year and a bit ago. Did we change anything? So if you bring this stuff up to anyone and ask them, listen, there seems to be a problem with TCP, what should we do about it? You're going to get one of 5 different answers. Either you're going to say, what do we do about it? And you're going to get an answer that's something like, well, that's probably going to happen. 2, you may get somebody to tell you, we don't do anything. This is what it is, to your point. We have TCP. This is a symptom of TCP. It's worth the benefits to still use a single connection, and we're going to keep using a single connection. It's better overall in the long term. That's the second answer. The third answer is one I just heard 2 days ago, and it's very funny to me. And it's a couple of people are starting to recommend sharding with H2, which is really funny because the entire idea, sharding is when you essentially create a situation where the browser ends up opening multiple connections. And it'd be very ironic if that actually becomes a best practice. After all this time, we will laugh about it. We will laugh about it, and it would be great. I don't know if that's happening, but when I heard it, I was quite amused. Maybe that's just an indication that I don't have an interesting life. The fourth thing you're going to hear is these 3 letters. Who's heard about this? Yeah, you have. I know you have. Okay, BBR is this like brand new congestion avoidance algorithm, spearheaded by, of course, Google. And I'm not smart enough to understand all the intricacies, and I've tried to read specs like this before, and I just can't get past like the 3rd word. But the idea is that it's a better congestion control, congestion avoidance algorithm, as opposed to Cubic, which is the default Linux congestion algorithm today. it works differently. It essentially like pulls the stream for bandwidth and RTT information as it's going along to tweak itself. And in the blog post where Google announced this, they have a nice little diagram, a graphy thingy that shows what the benefit would be. And the idea is that a loss event doesn't cause as much trouble on the connection as it did with cubic. Again, if you like reading, here's a list of things that you can read with a terribly unpunny word up top, the title up top. So this is like the new cool kid in town, BBR, and a lot of people are thinking about this as kind of the savior. Netflix tweeted about it. They published some numbers. They saw higher C-wins in their network. They saw a better throughput in their network, even with packet loss, which is kind of cool. Dropbox published something about it where they turned it on for a short period of time across a different, those are their clients' access bandwidths, and noticed some improvements, better throughput. I did some testing. I didn't do as intense a testing as I did with H2, but I did this thing with Catchpoint. Who uses and knows Catchpoint? A synthetic testing network. They have nodes everywhere, and they have a bunch of nodes in like people's homes, what they call last mile nodes. So these are relatively realistic conditions. I downloaded a 1 mega object about 400 to 500 times from a bunch of different nodes. That's what you see in the x-axis. This is the median performance of load time for that 1 mega object. So lower is better. So lower is faster. Blue is cubic, blue is BBR, red is cubic. And you'll see that the results are interesting. BBR is a lot better in certain places. It's not so good in some other places. These are medians. This is the geometric mean, which is like supposed to be the better average. This is the 95th percentile, where when it's good, it's really good. When it's bad, it's really bad. But be a little bit careful with looking at this because I only have like 500 data points per, so 95th percentile is like what, 15 data points. So that's not necessarily great. To that effect, here's the 25th percentile, also to take with a caveat. What's interesting is at the end of these downloads, we can do this thing at Fastly where I can actually pull some TCP parameters about what happened on that connection, including how many retransmits I had and what the C-wind ended up at. And then I saw some interesting things. This is where this is the average number of retransmits. And notice those big blue bars right there. The reason for this is one of the things that BBR does is BBR is very aggressive when it comes to loss events. So they actually will plow the network with retransmits because I think the main idea, again, I don't know this authoritatively, the main idea is a retransmit doesn't necessarily indicate network congestion. So we can be aggressive with resending some things on the network. And you'll see that here, this is where the C-wind ended up at the end of the communication. And with BBR, a lot of places, not everywhere, it was significantly higher than cubic. And the reason for that is when there's loss events in the network, cubic takes a big hit, and BBR just keeps plowing. And that is actually one of its problems, which I'll talk about in a second. I isolated just a few of the nodes, which I thought were really interesting, where the performance was better with BBR, but it certainly had more retransmits, and the C-wind ended up at magnificently high numbers. It's okay if stuff doesn't make sense immediately. The idea is that it's very different. It's a different way of looking at congestion events and network issues. But it comes with some caveats. There's a big discussion in the community on whether BBR is a good network citizen because of how aggressive it is. And in fact, somebody overheard, somebody had a conversation, and then the term network waterboarding came up, which I think is great, is a very funny term. I'm going to use it. And I think it's generally well understood that there's still work to do. This is a very difficult thing to test. It's a very difficult thing to test to see if one congestion avoidance protocol or algorithm is harming neighbors. That's a difficult thing to test. So we still have a lot of work to do. From what I understand, those who are doing the most work with it are aware of this and are tweaking as they go. In our network, and I can only speak for us on Fastly, it's available. People can play with it if they want, but we sort of give these cautions, and it's not on by default yet. So it's an interesting thing to keep an eye on, and certainly to keep track of as it develops. It's available if you're using Linux on kernel 4.9 and above. It's available there, so you can turn it on. That's the fourth thing they'll answer if you talk to them about TCP. The fifth thing I'm not going to talk about now. I'll talk about later, but it rhymes with Schwick. This, however, isn't the end of our journey on the yellow brick TCP connection. There's this other thing called coalescing. And coalescing is that thing that the spec allows you to use multiple domains on a single connection, or what the spec calls connection reuse. What's interesting here is what the spec tells you to do. It says, essentially, that if the certs match and the IPs match between two clients, so if both hosts are on the same cert, essentially, and the IPs match when you do a DNS lookup, you can use that connection to send requests for both hosts. That's what it says. However, this is a loose recommendation in the spec. It's only 2 sentences. So you can interpret this in a lot of different ways. There's a great blog post by Daniel Stenberg from curl fame and Mozilla that talks about how things are done between Firefox and Chrome. Essentially, read this. This is a great thing to read. Essentially, Chrome basically looks at this connection and compares certs, and if the IP is the same with the DNS lookup, Chrome does it the way you think somebody should do it. Firefox is aggressive, and Firefox essentially matches the cert, but if any overlap between IPs has been seen during like the lifetime of the browser session, I think, it'll coalesce. So we started noticing this on our network. We started having customers call and say, "The hell, man, stuff is arriving on a connection that shouldn't be carrying that request." Turns out it was Firefox, and it was how aggressive it was, and they were doing crazy, not out of the ordinary things with DNS. Like imagine when you do load balancing with DNS. DNS basically ended up having a lot less control. You end up having a lot less control where things go with DNS. So this is something to be aware of, and we're very careful with this, and we've now educated our customers. The education's out there, but if you're thinking about the benefits of coalescing, understand how the browsers work, and this is a great place to start. The protocol itself gives a mechanism against this. It's a new status code that H2 introduced called 421 that lets you, if a request comes in over a connection, you don't want it over that connection, you respond with a 421 that basically tells the client to go away and do another connection. The problem is this is a round trip and it's too late. You've already sent the request, you gotta wait a round trip to get the response back. Enter the brand new origin frame, which I think just got ratified, I think. The origin frame is a new thing. We're actually excited about this. And basically what it does, it's a brand new frame. And in this frame, it's an opt-in service. In this frame, you essentially dictate to the client what domains are eligible to be coalesced over a connection. So and it's an optional frame. If you don't send the frame, it defaults to 7540, whatever the RFC says. If you send an empty frame, which you're allowed to do, it defaults to the SNI, the name in the cert. That's the only thing that can come over this connection. And then if you send an origin frame that's got domains in it, that's your way of telling the browser that it can send requests from those domains over this connection. And you can tweak that. You can keep sending a different list. Like you can send origin frames in the middle of a connection. But check this out. It actually tells you, I'm exaggerating it a little bit here, so here's what the spec actually says. It relaxes the requirement to do a DNS lookup when the origin frame is in use. What this means is essentially this is opening the door to people sending you requests over a connection without a DNS lookup. So that is a trippy thing to think about. Now, it's possible that this may be the way of the future, and I have other indications in a second that this may be the way of the future, but that's a trippy thing to think about. Whether the browsers will fully ignore DNS or not, it remains to be seen, because it doesn't say what they should do, it just sort of relaxes it. So that part remains to be seen, but this would be really interesting. So if the origin frame is in use, it's possible that based on the client implementation, we actually don't do DNS for those domains that are listed in the origin frame. What this means essentially is that the connection itself is becoming essentially an authoritative and a secure context for communication between the client and the server. And more things are going to happen based on this premise, that the connection is trusted, is authoritative, and it's the truth, it's the source of truth. Case in point, this spec, I don't know if you've seen this, this is a new spec. This is a spec that basically lets you push certs on a connection. So this will allow servers to actively push certificates to a client. So if instead of a client using normal TLS handshake stuff to get a certificate from a server, this, through an HTTP mechanism, can send certificates to a client, in essence, allowing that client to add more and more domains to the coalescing context. What's our conclusion for H2 and TCP? Well, we're not really sure about the performance benefits. It still is do it if it makes sense for you world, I think. BBR helps, but there's pros and cons. We should be careful about both those pros and cons. I would still recommend that you, on all things H2, try it out for yourself. Somebody coming in through the pipes? Try it out for yourself. I mean, it's a good talk, but it's not that good. To try it out for yourself and figure out if this is for you. At the same time, keep in mind that more and more shit's going to get shoved into that connection. And that connection is going to be a lot more authoritative and definitive going down the line. Okay, TCP aside, we're done with TCP. Let's talk about the big other feature that we went crazy over, which is H2 push. Everybody, myself included, was very excited about push. It is an exciting feature. And the basics of it, in case you don't know, is the idea is that you essentially push an asset to a client before the client's even asked about it, because you as a server have some knowledge that the client's going to need it. Only servers can push, and this is an example of a server-initiated stream. So any push stream is actually an even number one. If you remember, the odds are client, the evens are servers. It's a hop-by-hop property, so you can't push through a proxy. You can push to a proxy. And there's a special frame for it. There's a push promise frame that essentially governs the way a push works. And here's how it works if we were to do really high-quality animations. You have a connection. The client sends a headers frame with the index.html. The server knows that to render index.html, there's some other asset that the client needs. So what it does is it sends a push promise frame with some CSS file and says that I'm sending you this CSS file. And what's in that push promise frame is the would-be request headers that the client would send if it was to naturally request that asset on its own. Then what happens is it sends headers and data frames for the HTML that was originally requested and the CSS that's being pushed. So what happens here is that request for the CSS never happens. And this is the promise of push. I'm sending you stuff before you even know it, before you know you need it. The only rough requirement, it's not a requirement, it's a suggestion, is that send the stuff that references the thing that you're pushing before you send the thing that's being pushed. In other words, send index.html, which has a reference to css.css, before you send the CSS. That's the only rough recommendation. So this is the mechanism. The protocol provides this mechanism, and it's got lots of rules around it, lots of ways to do it. There's a big discussion then of what do we push. There's been a lot of discussion over this, and initially a lot of people looked at this as a good replacement for inlining. And the bad thing about inlining was that you would put everything in HTML, probably couldn't cache it on the client, or you couldn't cache them as good as you could. You can cache the HTML as long as you can cache the individual assets. So if you inlined, you lost the granular caching of each of the objects that you've inlined. With push, you get both. You get the RTT benefit and you get caching because each of those assets being pushed has its own caching metadata. Google wrote a pretty good paper on some rules of thumb. Facebook got creative and figured out some things with your feed with push. And Fastly's Patrick Hammond did this talk about time to first meaningful paint and using push for that. Very, very good talk. I would highly recommend that video as well. What's the way we push? Well, the common way is the ling header with the rel equals preload attribute. And this, which is part of the W3C preload spec, was essentially seen as a good trigger from a server to an intermediary to trigger push to a client. So it kind of looks like this. So when proxies that support push see this from an origin, they'll know that they need to push css1.css to the client. But link rel preload already kind of means something to a browser. For those of you who are familiar with this, link rel preload is essentially a trigger for the browser prefetcher. It invokes the browser prefetcher, which is a good performance thing. You should use link rel preload to invoke that prefetcher. But basically what's happening is those functions are being conflated, and there's an assumption that if the browser is going to use the prefetcher to grab something, it's probably a good idea to push it. But if you read discussions online, you never come away with a sense of confidence that this is really a good idea. There's a lot of like, I don't know. There's a lot of back and forth. So, and one thing that actually exacerbates this lack of confidence is the preload spec adds this other attribute called no push, which says, look, if you know that you want the link rel preload to go all the way to the browser, you don't want it to do a push, put this no push on there, and an intermediary shouldn't push this, which sort of implies that there's a situation where you want one and not the other. But they don't give the other side. They don't give a mechanism that says only use this for push and don't send it to the browser. So at Fastly, we added it ourselves, much to the chagrin of people who don't like X dash type of things. We added this. This is only a Fastly thing. I have no idea if or how other proxies and CDNs do this. We added this because we thought that this stuff should be in the hands of the implementers, and we want to give you all the levers that you can. This hopefully will also be available from others. What are the benefits of push? Well, it's best shown in a waterfall. Here's the waterfall. Up top is not push. This is an HTML that references for CSSs. And on the bottom one, that's us pushing those four CSSs. What you'll notice essentially here is that you get one round-trip benefit out of this. Why is it just one round trip when I send four things? Well, it's one because we built H2 to do multiplexing and interleaving and concurrency. So the browser can actually send all those requests at once. So it's not send and wait and send and wait. You can do all that stuff at once. So what happens is at the end of the day, you get a one round trip, one RTT benefit. Now that's only the case if you look at the green bars up here. That's only the case if the HTML is really just as close to the client as the assets are. What this translates into, if you're talking about CDNs, is caching the HTML at the edge. If the HTML is cached at the edge, which is right next to where the CSS is cached, then what you basically get is a single round trip benefit from push. Now, I love caching HTML at the edge, and I will talk until I'm blue in the face trying to convince you to do it. And I have talks. I can even point you to those. I will come to your company and do talks for you. I am a big fan of this, but sometimes that's not possible. So this is cool, but look at this use case. Here's a use case where you have some sort of surrogate in the middle. The request that can't be cached at the edge goes all the way to an origin, and it takes time for the origin to render that response. That's what we normally call server think time. Look at the server think time here. At the end of this server think time, that's when the server sends the response, and in that response comes the link header that's supposed to trigger the push from the edge. The problem with this is this. Look at how long we wasted on the network. That's actually time where we could have sent things to the client. So that's wasted time. Enter a brand new RFC, 8297, for something called early hints. Early hints introduce a new status code, 103. And what a 103 is essentially is a way for a server to send some response headers before it has a response to send. So what it does, roughly what the spec says, is you can send some of the headers that you're going to send in the final response early, and then send them again when you have the body and the rest of the content to send. So this is what it kind of looks like. So you get the index.html at the origin, you ship out the link headers in a 103, that triggers the push, so the push goes out a lot earlier, and then you send the 200 with the actual content. You'll also include all those link headers in the 200, but because we've already pushed it, we don't care. But there's a problem with this. Look at that. So even though it got better, there's still an issue there, which is why we think it's a good idea to have some other non-header-based trigger for push, which would essentially allow you to do this, which is actually the best way to do this if you're trying to take advantage of server think time. We at Fastly call this async push. I have no idea if there's a name for it in the industry or if others do it. I just know we needed to do it because it made sense. It's really easy to do in VCL. We do a lot of our configs in VCL. I'm sure other pushers have ways of doing something like this through configuration, but the benefit of this becomes very obvious when you look at waterfalls. And that's basically what an async push waterfall looks like. And I did this by exaggerating what the HTML time is, just so you can see the benefit. So this is cool. So when there is long server think time, if you have a mechanism like this, you can leverage push. Take into account, though, essentially, if you do this, still what you're saving is the one round trip time, which is up to you whether you think that's good or bad. Of course, at the end of the day, none of this is this simple. And why isn't it simple? Because there's something called a client cache. And the client cache may have some of this shit in it already. Some of this stuff may already be in the browser cache. So the protocol gives us this mechanism through a frame called a reset stream to mitigate this. And what this means is if you get a push promise that says, I'm going to send you something, and that thing is in your cache, you can send a reset stream. And that says, don't send it to me. I don't want it. The problem is that's taking time. And stuff is already on the way. The server has already sent you stuff. So this is not really a very good mechanism. We appreciate it, authors of the standards, but this isn't necessarily practical. The second point, and probably a bigger one, is this. Look at these two waterfalls. This is a no-push scenario. This is a first view versus a repeat view, and because I come to Sergey's meetups all the time, and I know how to cache things and do performance stuff, I've tagged all these assets with really good cache control headers. So my browser caches them because I'm very, very good at that stuff. So what happens in my first view takes time because the first request is dynamic and the rest of the stuff needs to get loaded. But because my assets are in the cache, my repeat view only has the request for the HTML. Look what happens with the pushed version of this. The pushed version of this, I push a bunch of stuff. That's great. And then I go back, and hey, I push them again. Isn't that great? The reason for this is a complicated one. And Yoav Weiss does this amazing blog post with pictures that his daughter drew. This is a great blog post that basically tells you what the problem is. And the problem is there's like 4 to 5 caches in a browser. There is a memory cache, there's an object cache, there's a push cache, there's a worker cache, there's caches, many a cache. And they don't necessarily talk to each other. So the push cache, which is responsible for getting this stuff, doesn't actually talk to the HTTP cache. So the browser doesn't even know the stuff is in the cache necessarily. So this is a problem. Enter cache digests. Again, a new proposed standard, which is a cool proposed standard. And the idea behind this is an H2 frame that will communicate from the client to the server roughly the contents of the cache. It's an indicator. It uses filters whose names are too complicated for me to say, but cool filters. It was a Bloom filter at one point, then it turned into something else. That basically give you the server an indication of what's in the client's browser cache, so you can push things sort of smartly. And that's a good way to sort of mitigate some of those issues that we have client-side with all the client caches. Kind of looks like this, but this basically tells us that we still have a lot of work to do for push to work. And there's no indication better than this article by Jake Archibald, who's like a Chrome guru, who sort of came across all this stuff, realized all this stuff, and wrote about it. And he also outlines all the caches and why push is so difficult to get work. So that is something I would highly recommend reading. So push is sort of a mixed bag. What's the adoption of push? How many people are using it? Okay, again, I don't know the world, but I have access to my caches. So what I did was I log into a cache. I'm going to show you the numbers. I'm going to show you the actual commands. And I sampled 30,000 H2 requests to see how many of them are push and how many of them are not. Any guesses to how many out of 30,000 were pushes? 5%? 5% is what? Out of 30,000 is 1,500? 150? 150? 1,500? Yeah? Okay. Any other guesses? 0%? Oh my God. That's ridiculous. There's no way it's 0. It's close to 0 though. So there's a bunch of pushes. I mean, there's a bunch of H2 requests, and there's 3 out of the 30,000. I did it 3 times just to see. So it's not like adoption isn't through the roof. And maybe it's because it's a mixed bag. So that's US West. I also did this on US East. And, oh, I went the wrong way. And it's, well, you can look at this and say, US East is using push twice as much. But you're right. So I think this is like 0.03% or something. I don't know. I'm not a math guy. So at the end of the day, when you look at push, it's interesting when you talk to, especially when you talk to browser vendors about push. I'm not convinced they like it because they had to put a lot of scaffolding in place to support it. I mean, it's a complicated mechanism that goes against everything HTTP has ever stood for. So it's interesting. It certainly seems to have some benefits, but I think the question at the end of the day is that one round trip that we gain, is that worth it? And if we actually allowed that 103, which is the link header, to be sent directly to the browser instead of to the intermediary, we can actually just do all of this stuff straight to the browser, and the only thing we gain is the one RTT at the end of the day across everything. So these are interesting questions to ask. I don't have any answers, and I would love to see more adoption. If you start using H2 and start using push and have great benefits, please let me know. I think it'd be interesting when we revisit H2 in a year. But that's a thing to keep in mind. And we've been pushing for 103 to the browser. We think it'll be really beneficial, and it'll make things a little bit easier to implement as well. And I think at the end of the day, cache digests are going to be interesting no matter what, because I've always wanted to know what's in a browser's cache. I don't know what the use cases are outside of push, but it seems like that's a thing that we can probably leverage. You have a question? Well, it's not actually the stuff in the cache. It's like an indicator, yeah. So that's a good point. I'm not convinced that's actually true. Yeah, I'm just not convinced the one round trip benefit is worth the complexity. Yeah, and I would say your point with the cache digest is a good one. You should chime in on the user groups because it's currently in the middle of being. I think so. It's a really good question. I don't know. I think the answer is that it's just not well understood. The benefits aren't well understood. It's on paper, it's great, but what do you push? When do you push it? How do you push it? Well, the how is kind of well understood, but the what and when seem to be sort of shaky. People adopt slowly in general, I think. I think it's just a combination of those. I don't know. That's, I think, a great question. I'd love to know the answer. And I know the browser vendors would love to know the answer because they have to do a lot of stuff to maintain all of this, and it'd be interesting to see if it's worth their times. But it's a good question. I don't like inlining because of caching. So I think you lose caching. My preference personally is 103 to the browser. That's what I would do. I would live with the one round trip up front and send a 103 to the browser that essentially sends the link headers to the prefetcher before the body. So you let the server do all the thinking at once and just get the browser to download earlier. Essentially separating the headers from the body. That's what I would do. Okay, we don't have, how much time do I have? Like 10 minutes? Let's not worry about that. I have a lot of content. Okay, tell you what, you get to tell me when to stop. Is this interesting? Is this like, is this okay? It's okay? It's good? We keep going? All right. God, I'm just a shill, just looking for the applause. Okay, we're going to talk about prioritization, which is another major mechanism and not a very well understood one in H2. The idea behind prioritization is that now that we're doing all this concurrency and all these things at the same time, we have to figure out how to handle contention. And prioritization, the mechanism, is a way to address this. There's two elements to it. There's a stream weight. Every stream gets a weight or a priority. And then every stream also gets a dependency, so streams can depend on other streams. And everything is dictated through headers frames and dedicated priority frames. So with a header frame, you can dictate priority, and with a separate priority frame, you can also dictate priority. And the spec says that it's a general suggestion. So it doesn't say you should follow this, but it's a good idea if you did. That's basically what the spec says. Now, it's best to show you this by example. It's all in a tree, so everything starts with a root node. In this case, if you have two streams, one with a weight of 12 and one with a weight of 4, what this means to the server is give 3/4 of your resources to stream A and get 1/4 of your resources to stream B. That's what this means. These are not my examples, by the way. These are, again, from that excellent book from Ilya. Here's another example of dependencies. C is dependent on D. Here, basically what the tree is dictating to the server is get done with D before you start with C. That's what this means. And actually, the weights in this case don't matter because there's no sibling. Let's get more complicated. Here's one where you have both dependency and priority. In this case, we're saying do everything, give all your resources to D, and after that, give all your resources to C, and after that, give half your resources to 3/4 to A, and 1/4 to B. And the final cool example is a more complicated one, obviously. Give all your resources to D. After you're done with D, give half of your resources to E and C. And after you're done with C, do that 3/4, 1/4 thing between A and B. Priorities are dictated by the client. And what's really interesting is when you see how clients built these trees. And somebody did this work. So here's what Firefox's tree looks like. Firefox's tree is a complicated one. It really looks like a lot of data science and smart academic work went into it. It starts with these sort of 5 streams, 6 streams if you count the 0 stream. And these are actually like ghost streams. They don't actually carry anything. They're just sort of there as root nodes. And then all the objects sort of live under these. And they get their different priorities. There's both priority, there's dependencies. The colors indicate the type of object. I think the gray one is HTML. The green ones are images. The blue ones are CSS. And the yellow ones are JavaScript. And it sort of does a lot of work to maintain this tree, and things fall in and out of this tree. Edge has a different approach, which is everything is the same. So in this case, there's no dependency, and everything is a sibling, and they all get the same weight, so actually no priorities either. Frederick in our team, who does a lot of H2 work, did a presentation where he looked at Safaris. He works on H2O, the server we use, and he put some tweaks in there to sort of look at it. And he mapped out what roughly the tree looks like for Safari. And then a couple years ago, this is what the Chrome tree looked like, which was basically priorities, so they all have different weights, but no dependencies. That was a few years ago. Today's Chrome tree looks very different. Today's Chrome tree kind of looks like this, and the way we graphed this out, Frederick, again, wrote this very cool tool, that's the link to it, that takes out, you can basically copy and paste the trace from the Chrome net internals tabs, paste it into this tool, and it gives you what the tree looks like. And this is what the tree looks like. This is a tree for that 100 object page, so it's just 100 images, that's it. And this is actually not a good representation of the tree. This is the actual tree. So it goes like this for a while. And this gives you the impression that there's some stuff happening at the same time, because or I at least, think that this is time-based, but it's not. That one little green thing up there is the first image, then there's 46 images, and the 47th one starts the 4th branch. So essentially what's happening is everything is dependent up this way with exclusive dependencies. What's wrong with this? Who can tell me? Now that you're experts in prioritization, because we talked about it for 3.5 minutes, who can tell me what's wrong with this? Yeah. Yeah, what you're losing is interleaving. Basically, you can't do anything at the same time anymore. What this is forcing your hand in is waiting for every image waits for the previous one, and then every image waits for the previous one. So what you're doing is you've actually taken away some H2 features. So there's no concurrency in this. Everything's coming in one after another. In fact, there's a bug open about it in Chromium. And this has been open for a while, and there may be reasons why this is the preferred way. There's a lot of discussion over this, so read over that thing. I think what's interesting here is that, again, like most other H2 mechanisms, this isn't like we're learning as we go, and we're going to learn some more about priorities as we delve into this. But I was surprised to see Chrome do this. It seemed anti-intuitive. But it's an interesting thing to keep in mind, and I'm going to keep using this tool, which is from Frederick's tool, to keep an eye on what Chrome is doing. Some of the things to look out for in priorities is these things called priority hints, which was natural. It's only at a discussion level right now, but interesting to keep an eye on. The idea is you give the developer, the client, ways to dictate the priority. If you've ever looked at dev tools, you'll see that there's natural Chrome priorities, high, medium, low, I think, is 3. So there's a bunch of discussions on can we dictate that with like tags inside, like image tag, for example, dictate as priority. And it's very early days. They haven't figured out what this means when it comes to what the priority dictated by the developer translates to H2 priority. It's super early days, but this is essentially a letter of intent. But interesting thing to keep an eye on. That's priorities. Last feature we're going to talk about is HPACK. And HPACK was the companion RFC to 7540, which was 7541. And HPACK was the header compression feature of H2. And it was supposed to address the bloat problem, the header bloat problem that HTTP1 had. It has 2 different mechanisms. One, all the headers and values are Huffman encoded. And there are tables that are indexes, essentially, on each side. There's two tables. There's a static table, which is defined by the RFC, and it's hard-coded. It never changes. It looks like this, and it will always look like this. You can't tweak this at all. There's a second table called a dynamic table that the two sides build as the connection progresses. And things go into this dynamic table, and they fall out because it's a FIFO table. The way that when I was, like, the clearest it was to me is when I was looking through, on a casual Sunday afternoon, I was looking through some Wireshark captures. And I was looking at how things are indexed. And I was looking at the user agent. So here's the user agent. This is the initial indexing of the user agent. Notice that it uses index 58, which is in the static table. This puts this header into the dynamic table. It puts in the dynamic table at index 70. And then it stays at index 70. And then it falls down to index 71 because something came in front of it. And this is going to happen throughout the lifetime of the connection. And at some point, this is going to fall out. It's got to go back in again. What's interesting is there's no ACK mechanism. The two sides are doing this independently of each other. So they got to be really, really in tune. Is there a performance benefit to it? Well, I think you probably know this intuitively, but it's nice to see it. There's a benefit when you're talking browser to server, because basically all you're sending from a browser to server is headers. But is there that much of a benefit from server to browser? Well, there's a little bit, because you've got rid of a bunch of headers and turned headers into indexes. But most of what you're sending in that direction is body, so your benefit is slightly less. This was, just as much was said by a Dropbox paper that showed egress versus ingress benefits when they turned this on. So that's the benefit, so expectations there. Some things to know. The default size of this table, of the dynamic table, is 4K. And when I did this talk a year and a bit ago, browsers were all using 4K tables. This is the CSP header from Twitter. How big is this? What? So that thing, if it was ever to get indexed, essentially it would flush the table. And that's what would happen if it was indexed. It turns out that Twitter actually explicitly says don't index this, which is a mechanism that HPACK allows. So the biggest header actually doesn't take advantage of the compression, which is interesting. The compression context is per connection. So if you are to start a second connection, or if you're to drop this connection and start a new one, the entire dynamic table gets wiped and starts from scratch. And if you ever do sharding, you can't share context across the tables. You can't turn it off. And there's a paper that says it can kind of be an attack vector. So somebody figured out how to attack it. It's also slightly headline blocking on its own, right? So when you send a header before it gets indexed, you can't reference it until you know that it's been indexed on the other side. But TCP hopefully takes care of that. Some things have changed. It's now, I think this is Firefox, 65K dynamic table. Well, that's cool. That helps. I think Chrome does the same thing. And when I was looking at this, I realized that I actually misunderstood the way HPACK works in the following way. When the connection starts, there's two static tables, one on each side. The spec says that you can, like I just showed you, you can communicate the size of your dynamic table through this setting, header size. So what that does is that basically says that the header size, the dynamic table size of the receiving side. Point being that there's actually two sides. There's a decoder and an encoding, there's a decoding and an encoding table on each side, and their sizes are dictated independently. So the browser may say, I'm going to be able to build a table as big as 65K, and the server can say, I'm going to build a table as big as 4K, and they have to sort of match on the other side. This is probably not that big a deal, and it's only going to be an issue with huge cookies. I think that's the only time this is going to be the case. And it remains to be seen whether the last 5 minutes of our time together is actually useful to you. But there's no question that you are going to be the smartest person at the party. When you bring up HPACK and you're like, let me tell you about compression in H2, you're going to wow them. But these are things to know. Like, you got to leave here knowing some things that you didn't know before. And I hope they don't push out things that are useful from your head. Let me finish up with some tools and resources, things to follow up on. I know you're all very excited about H2 right now. Some things to follow up on. This book is amazing. I will never lose an opportunity to push it. If you use a browser, there's this little add-on that tells you what sites are H2 and aren't. It's available both for Chrome and Firefox. I got addicted to this thing. My eye just always goes to it. The dev tools are in a better place now than they were before. and you can now see a bunch of H2 stuff in DevTools. Of course, I will not go without mentioning Wireshark. You can decode H2 with Wireshark. This is the way to do it. There's basically a way to tell the browser to write its keys to a file that Wireshark reads, so you can decode it. Curl supports H2, so you can use curl to go to H2 places. And probably the most important thing I'm going to tell you today, after HPACK, of course, is that curl now also has a way of being decoded with Wireshark, because they also write to that file that Wireshark can read. So actually this happened just 3 days ago, looked at a curl request in Wireshark. I know, it's really, really exciting. There's another tool, curl-like, called NGHTTP, which models a lot of stuff out of Firefox. I think they're actually using the same engine. I'm not sure about that. Shows you all the internals of what happens when you make an H2 request. And there's a bunch of others. There's actually the working group has a bunch of tools that's growing. There's some tools. I don't think we're where we need to be. There's still room for more tools, but we're getting there. Okay, let's finish up by some pontification. What's going to happen next? So it is hard to argue that the complexity of HTTP sort of it grew a little bit before 1.1 and 2. Now, some people in this room, like Mr. Jackal, will probably say this resembles another graph, and that's why I feel this way. Maybe that's because I am a laggard and I just like old things. That's not true. I think it's fair to say that H2 got more complicated. That's not necessarily a bad thing, and at no point today is my intention to tell you that any of this is bad. We are in a unique place, and I talked about this last time we sat in the panel. We're in a unique place where we're forklifting the major communication protocol on the internet. This is not a painless effort, and it's a thing that we couldn't do for a very long time. What I don't have on this a highly articulate graph is the time that it took. I mean, you can use my age as a proxy. So it took a long time for us to iterate, and what we need to do now is iterate, and we need to keep iterating, we need to learn. It's not a bad thing that push adoption is low. It's not a bad thing that we don't understand some of these things and we're not using them. It's just that we're in the learning curve right now, and that's a good thing. So the community is hungry for data. So if you're curious and have data, just one too many, just have that data. The community wants it. Talk about it. If you see benefits, anecdotally, I heard just the other day that somebody turned on H2 and got 75% benefit. That's great. Tell the world about it. This is a great thing. So the world needs to hear it. We're not in a bad place. We're just in transition, and transition isn't always painless. So this is a good thing. Case in point, the next cool thing in the world, the QUIC protocol, which is the way I'm going to finish today. What's really funny to me, maybe because I'm just slightly skeptical, is imagine 300 years from now, a protocol archaeologist decides to look through what we're going through. It's like Indiana Jones of protocols. So he's digging through shit, and he sees the Holy Grail and the Ark of the Covenant, and gives them away, and he finds our specs and is excited about all the HTTP that we used. What he's going to see is about 20 years of H1, and then 12 minutes of H2, and then QUIC. Because we've become fascinated with QUIC all of a sudden, where H2 was the cool kid, now QUIC is kind of the cool kid. And it has its logo, it has its own logo. That's a pretty big deal. So one of the things I want to do, QUIC is in its early stages in development. So this would be the fifth thing somebody would tell you if you said, what do we do about TCP and H2? They would say, well, go to QUIC. QUIC is probably a long-term solution. So QUIC is an interesting thing to keep track of. But we are on HTTP for a while, and we'll get to QUIC, and it's an interesting thing to keep track of. And the first thing I'm going to teach you about it, and if you just take this away and nothing else is fine, we made this great decision with H2 where we didn't call it Speedy. Speedy was the Google protocol, and then we sort of took that as a baseline, and we made H2. There was no confusion what was Speedy and what was H2. There's a lot of confusion over what QUIC is. So the way the community is talking about it is GQuick and iQuick. GQuick is the Google version of Quick, which is this monolithic protocol, wholly contained, used on Google properties, for a lack of a better word, a proprietary protocol. Chrome is the only browser that supports it. Whereas iQuick is the standardization effort that's going to take that, just like we did with Speedy, standardize it, make it modularized, and have a thing that everybody can implement. The stacks look slightly different if you compare H2, GQuick, and iQuick. It's not Quick Crypto that iQuick is going to use. It's going to use TLS 1.3. It has an application layer, which will be H2, but there is a specific draft for mapping H2 to Quick. There is a thing called HPACK, which will be the HPACK for Quick. There's actually 4 standards. You thought H2 was complicated. There's 4 standards, 4 documents that the Quick Working Group publishes. Every iteration is 4 documents. They're on 9. It's still early days, but the promise of Quick is a lot of improvements over. So this is an example of iteration, right? We're learning and we're moving. So Quick promises us 0 RTT. So basically, you have no setup time. If you've been to a site before, you start communicating with data immediately. This is through TLS 1.3, but Quick has a way of leveraging that. It's going to use UDP, which sort of addresses all the headline blocking issues that we have. It'll allow us to do congestion avoidance, not in the kernel, which is where Cubic and BBR happen, but in the user space, so we can actually write congestion avoidance software. That lets us iterate quickly. It's one of the biggest reasons Google uses their version, GQuick. Everything's going to be authenticated, so it's good for security people. It's going to basically not allow middle boxes to do any crazy shit. That's a big part of this promise. And it will have connection migration. So if you leave Wi-Fi and go to LTE, you'll actually maintain your connection. It has a connection ID that's supposed to transfer. There's a bunch of quick reading because the 2 slides that I showed you are not everything, obviously. These are the questions I think we need to finish up with. Has much changed? Not much, but things have changed. I think we're learning. I think the origin frame is a good lesson. I think 103 is a great lesson. I think cache digests are a good way for us to mitigate a bunch of the push stuff. Coalescing, the fact that we're going to use the origin frame for coalescing, that's a great thing. We still have a lot to learn. There's no question. We still have a lot to do. I don't think there's any question. Quick will probably not fix everything. We'll probably expose new issues, but it's a good next step. These are all questions that we should be asking as we talk and explore about H2 more. But again, none of this is bad. It's okay. We're just in a unique position to be doing this. And we're kind of lucky to be in that position because most people don't experience this sort of overhaul in the way the internet works. Just so I can say we did 200 slides. That's all I have. I went 10 minutes over. I'm sorry, but I hope that was hopeful. Thank you.